Zone. Now it's done for Todd. He's working in LLNL. He's the main developer of Spack. And yeah, fight.
All right. So yeah, when Jordi invited me to this meeting, he didn't tell me that it was going to be a cage match at the end. So yeah, I'm the developer of Spack. This is a tutorial that we gave at Supercomputing, and I guess I'll also try to highlight the differences between Spack and EasyBuild. Spack is sort of a project that I started in, I guess, 2013, out of mostly rage at how hard it is to build things for supercomputers. And so, a lot of the motivations are similar to EasyBuild. But, I think we've taken a slightly different approach, so I hope that you can at least get that out of the presentation here. All right. So what this is going to be is I'm going to do some presenting, and then there's a couple demos. So I only have time really for the basic usage demo and for how to make a Spack package. So there's no module configuration stuff like we do in the full tutorial. But that's available on the website. So if you want to see more about Spack after this presentation, then it's all at spack.readthedocs.io. And then you can go to our GitHub repo there. It's github.com/LLNL/Spack. And you can also go to spack.io, which is sort of our main page, which has links to all of these as well. If you go to the GitHub page and you like Spack, then feel free to give us a star. And then we're going to use these links later on in the tutorial to download the materials. So to sort of respond to Kenneth's slide, who is this tutorial for and who is Spack for? It's not targeted just at developers. It's targeted at all sorts of people. It's a package manager. So it's for people who want to use software. It's for application teams. These are sort of, the application teams are kind of the bread and butter of HPC at Livermore. We have a lot of very large multi-physics application teams, and they function sort of like a user support team does at some of the smaller HPC centers, in that the application developers are actually deploying their applications on our systems all the time in their own space. And they have their own user bases and their own sort of support ticket systems and things that they use on the machines. And so we targeted at them because they have lots of dependencies. They can have 47, 70, upwards of 100 dependencies depending on the configuration of their code. We targeted this at package developers. So one of the complaints that I had, since my background is in performance tools, is that nobody ever wanted to use my tools because they were so hard to build. We would say, oh, if you use this thing, you can get more performance out of your code. They'd go and download the tool and they'd try to use it, and they'd be like, well, I don't need performance that badly. And so that was sort of a frustration for me. So I wanted a way to give them the performance tools more easily. And then finally, we do target user support teams at HPC centers. The Livermore support team uses Spack to install both one-off builds of things for users and also to manage the RPMs that we deploy on the machines. So we actually use Spack to generate RPM packages that we deploy with LMOD on our systems. So there's a lot of people that this targets. This is probably the key difference between EasyBuild and Spack, I think, is that Spack is really targeting combinatorial complexity. We're trying to make it so that you can build any version of the package that you want. So it's not necessarily a fixed distribution in the same way that EasyBuild is with fixed versions. It's lots of different versions. So here's why. Our developers are constantly experimenting with their codes. They rely on 48 different third-party packages. This is just for one of Livermore's codes. 3 different MPI versions, 3 platforms, 7-ish compilers that they care about, and maybe 2 or 3 different versions of the different packages because certain packages are not compatible with other versions of the same package. So if you take that and you multiply it out, that's like 7,500 different combinations. And if I included more pieces of software that we care about in HPC, it could get even bigger. So we're trying to use Spack for the US Exascale program. And I think when we combined all the factors that they had with their application stack, it was like 1.2 million combinations. And this isn't including things like build options and other stuff that can go on the package. So it's on the small side. Spack is designed to let you sample that space. So we want to let you build an arbitrary point in that space with a special syntax and reliably install the package. So the other reason that we built Spack is because there is no real production environment in HPC, or at least I don't think there is. When we talk to application developers, at least in the US, they run across many different sites, and they might be running in someone's home directory if it's a developer. We might be running at Livermore, LLNL, Sandia. We run at all 3 sites with our codes. Different MPI implementations, different compilers and dependencies. All of these are different across different machines, and so you sort of have to be able to build in all these different environments, and the code has to be robust enough to do that. And that's a tall order. And so, there isn't really a production environment in HPC, and I think this is sort of a problem. But, if this is how it's going to be, we at least need a tool that lets us exist in this environment. So here's how the tutorial is going to go. This is the overview. I'm going to talk about some basics of building and linking. I can probably skip over some of this for this audience. This is for the supercomputing tutorial where we're sort of trying to get people acquainted with what exactly is Spack doing. There's a little bit of a talk part on Spack basics. There was going to be a coffee break, but we've already had that. And then I'm going to do a demo of sort of the basic usage, talk about what's Spack's model internally, how does it model dependencies, what is it really tracking, and then finally I'm going to show you how to make your own Spack package. So that's the roadmap. And I think why use this tool? Well, you can use it as a distribution mechanism to build large software packages. We also use it to automate testing. So with Spack, our teams have been able to test with more than one compiler, more than one MPI implementation. We had one of our production teams, with one of the ones with 47 dependencies. They were able to build 36 different versions of their code with different dependency configurations and get the bugs out of the code before they really started using Clang in production by just swapping Clang into the build. We let you swap compilers very easily with Spack. And then you can leverage the work of others to build, to use shared build recipes. This is something that really bothered me because I had a bunch of students who were working on my tools. And they would just do the same things over and over again. Every time they would get spun up on an HPC system, they would have to do the same build. So Spack is intended, like EasyBuild, to be a repository of package recipes. I think one difference with Spack is that we have one recipe file per package, whereas EasyBuild has a bunch of different configuration files for builds that have been done. But you would have to make another one of those configuration files if you want to make a new build. And then finally, it's a distribution mechanism. So I think all of these are good reasons to use package managers in general, so either Spack or EasyBuild. And so please don't build things by hand just because the majority of the HPC folks do it. Consider using some of these tools because it's going to make your life easier. And I think without more automation, HPC is not going to be a real production environment. Okay, so if you want to try out Spack, or if you want to just get it going on your system, go to the GitHub site and you just say git clone that URL and source the setupenv.sh that's in the directory. We'll do this together later. If you want to follow along, you can, or if you want to just watch the demo, that's fine too. One of our goals with Spack is that you shouldn't have to install the installer. So the idea is that once you clone it, it should run for you, and it should be able to pick up the compilers that are on your system and work with them without a lot of setup. So you only have to do those 2 things, Spack install HDF5, and it should be able to build HDF5 for you. And if it doesn't, then we should put your platform in our test suite and make sure that it works. Right, and I will talk about these other options later. So you can do install HDF5, but we also have a syntax for setting different configurations for things that you install. Also, like EasyBuild, Spack has a pretty booming community. In 2015, Livermore was pretty much the only site using Spack, and so that's this line here through these plots. What this is showing is lines of code over time in our packages. So these are the actual contributed packages from other organizations, and this is lines of code over time in the core of Spack, so the actual package manager part. And what you can see is this is when we presented our SC15 paper on Spack. And that seemed to get people interested, and we started getting many more contributions from different places to the point where now we have over 140 contributors or something on GitHub, and over 40 organizations are actually contributing to Spack. I would say that we are getting way more than we put into it out of Spack just because of these contributions. Like if you look at the packages up here, we're writing less than 20% of the packages these days. And we're not even the #1 package contributor. This stripe up here is Argon. And they've written a bunch of packages for us too. So it's been really rewarding because now we don't have to come up with build recipes for those things or manually install them on our system. We can just use what's in Spack. And in the core, we're also getting contributions. So Livermore still writes the vast majority of the core. I guess that's mostly me and also some people on my team at the lab. But EPFL in particular has committed a whole lot of stuff to the core. So they did the module support, they integrated LMod, and they did a lot of stuff to make Spack work in their production environment. So that's what you're seeing at the bottom here. And we're committed to sustaining the ecosystem. I think the lab in general, the management thinks that we get a lot out of this tool and that we get a lot out of the community. So we're willing to put in developer time to keep this thing working so that we can sustain this. Because I think if we don't, we may have to invest a little more to get this much growth out of Spack, but I think it's worth it because of what you get out of it. So if you need to make arguments to your management about why they should support open source products for more than just your institution, this chart has worked well for me. And then here's just a few examples of use cases of Spack outside the labs. So ARM, I discovered, is actually using Spack to test their compiler suite. So they're doing regression tests. The LIGO collaboration and also some folks at CERN are using Spack. Intel is trying to use Spack to package machine learning software for HPC. And we have, there's a large group at CERN, Fermi, and Brookhaven, the high energy physics group. They are using Spack to package up some of their applications. And they're trying to replace an older build system and development environment with Spack. Oak Ridge is working with us on Spack for our Coral deployment. So we're getting a big Power 9 GPU system at Livermore, and Oak Ridge is going to have a very similar machine with probably more GPUs than our configuration. But that's going to be really useful because we're kind of the only 2 sites with big machines like this. And so we can share the burden of getting packages deployed on the new architecture, and we're already doing that on the early access systems that we have with Power 8s. And then finally, Kitware is collaborating with us on Spack. We have a subcontract with Kitware to do things like modify CDash so that it can display Spack builds, and also they do some core development. They added things like dependency types to the core, and that's been a really useful collaboration as well. Working with Kitware is nice because they have a lot of other contractors, and so we're hoping that that will lead to other folks using Spack by recommendation through Kitware. We are not the first tool to automate builds. Neither Spack nor EasyBuild is. There is a long history of package management that goes way back beyond what we're doing. Gen 2 has been doing this kind of stuff for years. BSD ports before that. I think having repositories of package recipes has been around for a long time. I would say the things that inspired Spack most would be the so-called functional package managers. So Nix and Geeks are, they were sort of the first package managers to do cryptographic hashing of different configurations. And so that's one of the things that Spack uses to allow you to build arbitrary points in that combinatorial space and sample a build. We're able to version it with a hash. And I'll describe a little bit more about how that works later. But we borrowed that. We're not doing the binary hashing that they do. We're actually hashing the metadata. So it's a little less strict than what they're doing. But we think that that's the right measure of reproducibility for HPC, where we have so many platforms and we're not just doing Linux. The other thing that probably inspired Spack was Homebrew. I like using Homebrew on my Mac. It's easy. The packages are very easy to write and very easy to contribute to. So the Spack package format will look very familiar to you if you're used to writing Homebrew packages. The only difference, one main difference is that Spack packages are written in Python. And we made that choice because it's just a language that will get much more adoption in the HPC community than Ruby. Oak Ridge tried to deploy a Homebrew clone called Smithy that was essentially, it was written in Ruby. They had a really hard time getting their developers to write packages for it because they didn't want to pick up Ruby. And then obviously EasyBuild. I actually started, people have asked me this, they said, did you know about EasyBuild when you wrote Spack? I actually didn't. And then I discovered when I started writing Spack that EasyBuild already existed. It did not do quite what I wanted, so I kept working on my project because I was already pretty far along. And so now both of us exist. And then finally, Hashdist is also another tool that's sort of loosely inspired by Nix. That's out of some folks from the Army Research Lab, and also, I guess now it's Andre at Los Alamos, and some Norwegian guy, Dag, which is kind of funny because his name is Dag, and he writes a system that deals with DAGs. So, you know, it's interesting having conversations with him about this stuff. Okay, so that's the related work. So, you know, I just want to emphasize we're not the first people to do this, but we think we're the right design point for HPC. All right. So, what's a package manager? And I think this is an important distinction because I get asked if Spack is sort of a replacement for auto tools, and frequently, or if it's supposed to replace CMake or something like that, and it's not. I would say there's 3 levels of things that you should be concerned about. Low-level build systems like Make and Ninja deal with dependencies between individual source files and objects in your one package, in one project. High-level build systems like CMake and AutoTools, I think their main reason for existing is to handle all the complexities of shared libraries across systems. And they also do things like generate makefiles and manage dependencies among files in one project. CMake does some things like the CMake external project stuff. It lets you build external dependencies for one project, but I would say that package managers are more geared towards managing entire ecosystems of software. And they're managing dependencies at a much more, I guess, formal level than what external project or things like that in CMake would do. So you can view something like Spack or EasyBuild as something that manages the relationships between packages. It manages getting them installed in a consistent way. And in the case of things that actually build projects, Spack and EasyBuild drive the build system. And so we're basically calling into CMake or AutoTools or whatever the build system of the package would be in order to get it installed consistently. Package managers also include binary package managers. That's something that we're looking into for Spack, is secure binary packages where we could actually ship an optimized binary for different platforms. We're expecting to have that integrated by later this year. We just have to add the security. The CERN guys have already implemented the main relocatable binaries for us. But this is going to focus on the source aspect. If you're comparing Spack to things like RPM or Yum, those are pure binary package managers. You write a spec, a build farm goes and builds the package, and they're mostly concerned with getting the binary onto the system. Whereas I think systems like Spack are end-to-end. You start with a source description, and when we add binary caching to Spack, it's going to be as a sort of cache. It's not going to be as a whole separate part of the system that's sort of separate from the source management part. So hopefully that helps. I don't think I need to talk about the differences between static and shared libraries here because everyone's an admin. Spack was also designed to deal with nasty ABI compatibility issues in HPC. Maybe this is second nature to most people here, but if you do look at binary package managers like Yum and RPM, they assume binary compatibility between different packages. At HPC, we assume API compatibility for things like MPI, so you know that the same source can build with any MPI version, but they're definitely not binary compatible. So if you build one version of a package with one MPI implementation, you can't just swap out the libraries underneath it, it'll break. And I think that's true for lots of things that we use in HPC, like Boost, lots of Fortran codes, lots of C++ codes. All of those things are ABI incompatible. And so Spack is designed to manage that because we saw a lot of people at Livermore running into problems where they would just get symbol mismatches between their codes. All right, and I'm going to talk really briefly about 3 major build systems. So these are the main ones that this comprises most of, I'd say, Spack's package stack, unless you count the Python part. There's Make, CMake, and AutoTools. And this is pretty much what you're writing when you write a Spack package, is the instructions for a system like this to build it. So if you write a makefile, the typical procedure that you go through to do that is edit the makefile. You probably say make, provide a prefix somehow. Maybe you have to patch that into the file. There's really not configure options beyond just editing the file, so there's a lot of file filtering and patching that has to go on. And then there are some environment variables that matter. So we'll set things like CC, CXX, FC, and F77 to get the right compilers in the makefile, if it supports that. Otherwise, we're back to patching. Most makefiles support things like C flags, CXX flags, et cetera. Those are all in the make manual. Many HPC developers have not read the make manual, and so they do not know that these are the standard names for those things. So Again, if that happens, you're back to patching. So there's a whole lot of patching with the makefile builds. For AutoTools, AutoTools and CMake are both fairly easy to integrate into package managers because they have very standard ways to do things. For AutoTools, you typically type configure. It goes and does a bunch of tests on your system. You give it an install prefix, and it installs there, puts the software in the right Unix directory layout by default. You type make and make to build and make install to actually move the software into the prefix. Configure options. Generally, there's lots of them for HPC packages. We have lots of build options. They're supplied to configure. And you have pretty much the same environment variables that you do for a standard make build. So we'll get to this when we get to making packages. For CMake, typically you can build out of source with CMake, so you make a separate directory. You invoke CMake like you would configure. CMake can take all the configure options, and then it's make and make install again. And then CMake has slightly different command line arguments, but it actually respects the standard make environment variables. So you can, it's actually fairly simple to get a CMake thing to build because you just set the same variables that you would for an AutoTools build. All right, so that's sort of the summary of what you would be writing if you're writing a Spack package. This is the level at which we're operating when we're writing scripts for Spack. So when you actually go to install the Spack package from sort of a user's perspective, this is where Spack starts to differ from your typical package manager. We wanted it in the base case to look pretty much like RPM or Yum. So if you say Spack install MPI leaks is an MPI handle leak detection tool that we built at Livermore. This is unconstrained. You're just saying, get me some version of MPI leaks and make sure it works. That's what you would pretty much type with Yum, and you would get whatever version Yum has. With Spack, we provide a syntax so that you can be a little more specific about what you want. So you could say, I want MPI leaks at version 3.3. And you would just type that on the command line. If it knows about version 3.3 and where to get it, it'll go fetch it, and it'll install that. You can say what compiler you want it built with. So you can say, no, I want a version of MPI leaks that's built with GCC. And you can specify a specific GCC version 2. You can specify build options. So this will come in later when I show how to build packages, but this is one place where Spack and EasyBuild differ. Spack packages are parameterized. We have a lot of different build options that you can set on the different packages, and you can actually depend on particular packages built with particular build options. The parameter system runs through the dependency model. So if you require, say, a package to be built with MPI, then you can depend on that plus MPI. And that's the plus threads there. So if that's a build option, you would say plus threads to build with threads or minus threads to build without threads. You can inject custom compiler flags into your build on the command line. So you could say, I want MPI leaks at version 3.3, but I want this special set of compiler flags to get injected into the build, and we'll go and propagate that through all the compile lines in the package. And then we also support cross-compilation on systems like Cray and on Blue Gene. So you can say which OS and which target you want the package built for, assuming the platform you're building on supports that. And then finally, this syntax is recursive. And what I mean by that is you can put a caret on there, and so it's Spack install MPI leaks at 3.3, caret mpitch at 3.2. And so what that means is that you want that package built against that version of MPI. And so you're saying I want a specific version of the package and also a specific version of the dependency with a particular compiler as well. So essentially, this models the way that we build things at Livermore. Typically, I have a set of things that I want about the package, and so we want the user to just say what they want on the command line, and we fill in the blanks for all the other parameters for the build. Yep?
Do you have any way of auto-detecting the destination system, like, for example, vector instruction set or GPU architecture, anything like that?
Not at the moment. I mean, on the Cray, we'll default to build for the back end. That's what we do right now. So there's not that much auto detection in there right now. Okay. From a command line perspective, Spack looks pretty much like a regular package manager. You would say Spack list to get a list of all the packages that are available. We have over 1,500 packages now. And then you would say Spack find to see what you've already installed. And I'll show this in the demo. If you say Spack find, you get a list of packages sort of like before, but it's a little different. Notice that we're separating the output here by the architecture. And so an architecture descriptor in Spack is a platform. And so that's like Linux or Cray or Mac OS, or actually we call it Darwin. An OS descriptor, which is sort of how we represent binary compatibility with the particular OS that we're building on. It's just a string right now. We don't do much further than that for binary compatibility with the OS, but it's enough to separate, the different builds in our shared home directories at Livermore. And it would also be enough to distribute binaries for particular operating systems. And then a target at the end there. And so the target's generic x86-64 here, but it could be Haswell, Ivy Bridge, something like that, PowerPC 64, Little Endian, something like that. And so you can see that, and then we put the compiler up here. So that's the compiler that these packages were built with. We actually support mixed compilers, even though Robert said that you can't link things with different compilers. You can, we do sometimes. Usually it's GCC at the leaves and not anything much more complicated than that, because it does get very complicated to link things. So this is really showing you what the root is built with. And usually that propagates down through the DAG, but it doesn't have to. This is just one view of the stuff that's installed. And then we have other platforms and compilers down here. And then you'll notice that each of these installations has a version next to it. That's just partial metadata for the version. But we support, we allow all the configurations to coexist together. So you'll notice that there's actually 2 builds of Dyn State 1.2 there. And that's because they're configured slightly differently, and we're not showing it in this basic Spack find view. But you can query further to see how things were installed. And we allow things to coexist because we rpath them. And everything gets installed in its own directory and knows where its dependencies live by default. So if you want to see the full dependency configuration, you could say Spack find call path. You can see that there's 2 installed versions of that library. And then if you say Spack find -dl call path, will show you the full dependency. Well, not really the full dependency DAG, but it's sort of a tree view of it in this particular view. And the hashes next to those. The hashes are the unique identifiers for the configurations. And this allows you to see things like, oh, well, okay, when I tried to link against this version of call path, it didn't work. And that's because this one uses boost 155 and the other one uses boost 159. So you can go and introspect things at a very deep level once they're installed. And then finally, we allow you to build with the installed compilers. So we don't require you to bootstrap a tool chain or anything like that up front. We want you to be able to get going when you clone the repo from Git. So we'll go and detect the compilers on your system. And we put them in a YAML file in your home directory so you can customize them if you want to. The compilers are, right now Spack models a compiler as just the C and C++ executables and a Fortran 77 and a regular Fortran compiler. We are working on making compilers sort of more first-class members of the dependency ecosystem, but we want to preserve this auto detection. You can load a compiler from a particular module, and we designate what OS the compiler has to do with so that you know where you can actually compile with that compiler in the case of like a shared file system. And I'll demo how this works. So let me do that. Yep. Oh yeah, that would be useful. Is that working? Yeah. All right. Good enough. I think, yeah. Okay. Thanks. Okay, so if people want to follow along, you can go to spack.readthedocs.io. If people, can you guys? Oh, there's feedback. Maybe turn that one off. Or I could just use that one.
Yeah.
Maybe that's better. No? Do you want that on or off? Because I'll turn this one off. Does that work?
I don't know which one is working.
I think they're both working.
Right.
Okay, I'll turn this off. Yeah. I think this will be easier. Okay. All right. Okay. Can people hear me? Cool. So if you go to spack.readthedocs.io, there's a tutorial here, Spack 101. This is mostly what I'm working from. And then just go to the basic installation tutorial if you want to follow along. All right. And then I'm doing this on a Linux system at Livermore. You should be able to do it on whatever platform. but you know, the MPI leaks tool that I'm going to be working with is mostly for Linux, so I would run it on a Linux system. Okay, so here we go. So what I would do is, yep. It is, oh, which part? Web page? Okay. Good enough? All right. So the first thing you're going to want to do is just clone Spack like we showed before. And then just add Spack to your path. You can either do this or you can source the setup.env script in share Spack. So it's share Spack setup.env.sh if you want to do that. If you look at it on, can people see the terminal? Is that big enough? Yeah, okay. So I'm in a Spack directory. The first thing I would do is source share Spack setup.env.sh, and then you should be ready to go. It'll find itself. If you're on, if you're using C shell or TC shell, they can't find themselves from a source file, so you'll need to set spack_root all caps to the Spack directory location. Okay, so if you want to see what's available in Spack, what are the available packages, you can just say Spack list. I showed that before. There's no, and so that will show me all the Spack packages that are available. It looks horrible on this small terminal, but if I make it a little wider, you can get multiple columns. And there's about 1,500 of those. If you want to, query a smaller number of packages, you could say Spack list, say pi dash, to see all the Python packages that we have available. So that's how you would list things. And then if you want to install something, you just say Spack install, say libelf is a simple one because it has no dependencies. And so it'll go and download the thing. My archive's cached, so it doesn't have to download it from the internet. And then it'll be installed. And so you'll see down here that installed successfully, and it's in this particular directory. And so you can see that the directory, the directory structure is sort of under opt_spack. And then we have the platform here. The compiler, that's just so that it's easy to debug where the packages are. The real unique part of the name is the hash over here. So this is how we make sure that all the packages can coexist. All right. So you can, like I said, install with a different compiler. So if I want to install with the Intel compiler, I would say spack install libelf %Intel. Spack install libelf %Intel. And it'll build with the Intel compiler, which is a little slower. If you want to see the output during a build, you can just hit V, and it'll start showing you the build output. If you forgot to, or you can say install-V, and so we can watch this thing build. I'm going to go back over here and get a little ahead of it. And so you can see it's just going through a standard make. It's just driving the make system. And this does not take very long to build. Come on. Generally. There we go. And it's successfully installed libelf with the Intel compiler. Another thing that we can do in Spack is we can actually query what versions are available of a package online. So I can say Spack versions libelf. And if I do that, it actually goes out and queries the web page and scrapes it for URLs that look like the download URL and tries to find additional versions of the package that are available. And you can use that to automatically download and checksum new versions. There's a Spack checksum command for that. So there's a lot of integration there. And then, like I said, you can install custom versions of a package. So you could say Spack install libelf at, I installed 0813 because that was the default before, so you can see that here. If I want 0812, then I can install that, and it'll build with GCC, which is a little faster than ICC, at least on this system. So hopefully this will end faster. Yeah, there we go. And so now I've got another instance of libelf here, built with a different version. And I can do the same thing for the Intel compiler. So I can say Spack install libelf with Intel compiler at version 15.0. Let's say 6, because I think that's the one that's installed on this machine. And so now it'll build it with a slightly different version than before. And I'll let that go. Okay. So I guess we'll wait for this again. Okay, so there's another one. So like I said, you can use Spack find to see what's been installed so far. So if I say Spack find now, I can see all my different versions of libelf that I've installed. And if I want particulars about them, I could use find-d like I showed before. And I'll show you one more build. I can just say spack install libelf with CPP flags equal to -03. And so we'll build one more version with -03. And so one cool thing about this is that the compiler flags are actually included in that hash. So you could use this to do, say, a parameter study of different compiler flags with each of your packages. So if I say spack find, again, then I can see all these different versions. You'll notice that like I have these 2 versions of libelf 0813. If I want to see what flags they were built with, I can do spack find-lf to show the flags. And you can see here that one of these was built with sort of what the build system would do by default, this 0813, and this one was built with CPP flag set to -03. So all that metadata is actually saved with the package. Okay, so I've just shown you this, the spack find stuff. Let's do a slightly more complicated package. So if I install something that has some dependencies, like libdwarf actually depends on libelf or elfutils. So I'm going to go, and I think our default for that is elfutils. So I'm going to just say spack install libdwarf, and it's going to say installing libdwarf. Oh, but first it's going to install elfutils because that's the dependency. So we'll do that first. It goes through all the dependencies. Make sure that they're installed before libdwarf. And hopefully this does not take so long to build. If I want to look at the build output, I can do that. And there we go. So now it finished elfutils. Now it's building libdwarf. We can watch that happen.
What about compiler options? I mean, if compiler options are too aggressive for the dependencies, I mean, if you need O3 and O2 for the dependencies, which sometimes happens,
you can
use it in some way? Or
yeah, so the syntax is recursive. So if I wanted to type that on the command line, I could say spack install libdwarf with CPP flags equals -03 like that, and then I could say if I wanted to build it with elfutils like that, then I could also put CPP flags equals -02 here, and so that's how the syntax is recursive. It'll left associate. Yeah, and so you can take this to an extreme and write a whole lot of stuff on the command line if you want to. Yeah. And we have config files that you can use to set defaults for these kinds of things as well. All right. Yeah, so actually that's the next thing I was going to talk about. So is you can use the caret sigil. Yep, is there a question? Nope, okay. You can use that caret sigil to install different versions. I can say spack install libdwarf. I can build it with libelf at 0.8.12, which is one of the things that I already built. And I can say build that with the Intel compiler. I believe I did that with the GCC compiler. So just to be fast, I'll build it this way. And now I have 2 different versions of libdwarf with different sets of dependencies. So one of the libdwarfs is going to be built with elfutils, and the other one's built with libelf. And so elfutils is Red Hat's elf implementation, whereas libelf is the one from Germany. All right, so if I do a spack find-d now, I can see all the different versions and their dependencies. So you can see that libelf and elfutils don't have any dependencies, so there's nothing fancy there. But these 2 versions of libdwarf are coexisting together with different versions of the dependencies. All right. The other thing that you can do, I showed before that you can say spack find-l, and that will show you the short hash. And so this is kind of like Git. If you're used to Git hashes, we use slightly different characters. But you can refer to packages specifically by their hash. And so if I want to build libdwarf specifically with this version of libelf right here, then I can say spack install libdwarf, or if I type it right, libdwarf. And I can say depends on this libelf, and just put the hash there after a slash. And so that's how you refer specifically to one package. If there's something really specific that you would have a hard time writing out all the constraints for, you can just refer to it by hash. And so that'll work as well. So that's how you would reuse something that's already there, or force it to reuse it at least. Okay. So let's go. And if I want to see everything I've installed so far, I can just type spack find-ldf again, and I get, the full specs, or, most of the specs of all the things that I've installed. And so there's the CPP flags that you can see. You can see how they're differentiated and so on. Okay, so that's kind of interesting. Those are pretty simple packages. And I'm not going to sit here and build like all of Trilinos for you because it would take all day. But I can show you some other types of installs we have a -fake option. So you can essentially just build the directory structure that would be there for a yeah. Mm-hmm. So we have, we store the metadata with the package install, and we have a whole database that has all of the metadata for all the packages that are installed. Right now, we don't have a way to just spit it out and say, build it again on another cluster, but we're working on that right now. So we're working on essentially making it so that you can very easily take a subset of packages, export it, and reproduce it at different levels of granularity on different systems. So, I mean, right now, what you could do is you could just take the YAML, you could read it back into Spack, and then you could build from that. What we would support next is you could potentially reproduce the same stack on a system with a different architecture. So if you just read the YAML in straight, it would be tied to the particular platform. But I think what we would like to be able to do is rebuild a whole stack for a different compiler, or rebuild a whole stack for a different architecture, or something like that.
Okay, thank you.
Yeah. So yeah, we're working on making that easy. It's not easy right now.
So are you taking into account potential issues while you, I don't know, try to compile something into a more aggressive way, attending, I don't know, a subset of releases of a software compatible with a subset of releases with compilers? So for example, in Intel compilers,
mm-hmm.
I remember from release 13 to the 14, so they started to be more aggressive
mm-hmm.
In terms of optimization, and some packages started to fail and to pass all the test.
So yeah, I'm not going to show it here, but in the packages you can declare conflicts. And so if the package author says there's a conflict with a particular version of a compiler or a particular version of a dependency or something like that, you can write that, and Spack will yell at you if you try to install it that way. But you can also just leave it flexible if you don't know, and then it will let you try to build it, and it may fail. Yeah. Okay. All right. So if you install more complex packages, I'm going to do a fake install of HDF5. So I'm going to say spack install --fake HDF5. And this will get me, at least some more interesting dependency structure than what I've had before. So it'll go and install all the dependencies for HDF5. And this is where Spack starts to be useful, because this would take you a while to actually do by hand if you wanted to do this. And so now if I say spack find -d HDF5, I can see that I installed something fairly sophisticated there. Packages can also have variants, like I mentioned. And so if you type spack info HDF5, you can see what variants there are on HDF5. So this is kind of hard to see because of the screen. But if I scroll up here, it says here's HDF5. This is the description of HDF5. Here's the home page. These are the different versions that we can download and that we have checksums for. And then there are all these build options. And so these actually play into the hash as well. So if you change the build options, then that can be a different version that can coexist with other versions. In our case, we're going to play with this MPI option. And essentially, this is saying that it has an MPI option, it's on by default, and it can have the values true or false. So it's a Boolean variant. We can also have integer or list parameters on the packages. So like for the MPI implementations, people have added things like the network fabrics that are supported as a list of parameters. And so that can actually be a set of things that you support and other stuff. Yep.
How do you know which compilation options a software may have? Do you parse the .configure or something like this, or do you put this in a file?
Oh, so okay. So this isn't magic. This is people have to write the packages for Spack. And we do some stuff to get you started. Actually, there's a pull request right now that'll go and parse a CMake file and put variants for all the options. But for the most part, we didn't merge it because if you parse out all the options from configure or CMake, it's a whole lot of options, right? And most of them you don't care about in a package ecosystem. So essentially, these are ones that whoever wrote the package has exposed as common things, and they pick the names. And we try to standardize on names for some things throughout the stack. So like shared is a very common one for whether you want to build the shared libraries or not, or debug, things like that. But yeah, these are written by humans. And so you'll see how to do that once we do the packaging stuff at the end. Yeah. So I can say Spack install --fake HDF5 minus MPI. And so you can either say, so on the command line you can say minus MPI, or we also allow tilde MPI, although that will expand to someone's home directory if MPI happens to be a user on the system. So it can be a little, that's why we support 2 syntaxes for this. So if I do this, I'll get another install of HDF5, this time without all the dependencies. And if I do spack find -d HDF5 again, it'll show me both of them. So there's both HDF5 installs and what they depend on. And so you can see this one was built without MPI. It doesn't have an MPI dependency. This one was built with OpenMPI. It has the OpenMPI dependency. All right. So, and then the other thing that I showed you is that the syntax supports specifying dependencies. So I can say, I can build with a different MPI. So I can say spack install fake HDF5 plus MPI with mpitch. You'll notice this one's built with OpenMPI. So this will build another version that's built with mpitch. And so it's very easy to have all these things coexist. And if I run spack find -d again, then I can see now I got 3 versions. mpitch has significantly fewer dependencies than OpenMPI. Yeah?
These are empty shells, right? Because we're using -fake.
Yes.
How can you discriminate between an empty shell and an actual installation? Can Spack find show you which ones are fake, which ones are not?
Not right now, because we really only use the fake for demos. Yeah. So we use that. This is just for demo purposes. I mean, we could put something in there very easily that says, like, remove all the fake ones. But we typically just blow it away once we're done with the demo.
Todd,
Yep.
is the build log saved somewhere?
Sorry?
The build log? Like the
yeah, it is.
output of configure, make install?
Yeah, so if I can just do spack cd-i, like say libelf. Or actually, let me see which ones there are. Spack find libelf, or with a -l. And I can see all these different versions. Let me go to this one, spack cd-i. This goes to the install directory. So I can go straight to the install directory for this version of libelf. And in here, there's a .spack directory. And under that, we actually store the build environment, the output from the build, the YAML file describing the configuration. So if you cat that, you get the full provenance for the build. So, and then we also store the particular package.py files that were used to build this and all of its dependencies. And so if you look in here, you can see the actual package for libelf if you want to go and edit it again and see the source that was used to build this thing. So we store everything that's required to reproduce it, essentially.
Thank you.
Yeah. Okay. So let's see. And then we've also got kind of nifty command line tools for showing the dependencies. So you can say spack graph HDF5 minus MPI, and we'll show you a little ASCII graph of what that particular HDF5 looks like. That one's not very interesting, but I can graph the one that I built with OpenMPI, and it's a little more interesting. So we'll show a dependency graph with ASCII art. You can also you can output that to dot format and render it with GraphViz if you want. So this will just spit out dot format, and you could render that in your favorite graphing program. Okay. So HDF5, someone could build that by hand fairly easily. People do on a regular basis, but we can also install more complicated things. So one of the more complicated packages in Spack is Trailenos. Maybe it's not that interesting to do it as a fake install, but Spack will build Trailenos and has a lot of packages in it that depend on it. Trailenos has a whole bunch of dependencies. So let's do that. It'll sit there trying to resolve all the dependencies for a little while We're working on speeding that up. But there's hyper. Here's a bunch of other packages that are getting installed. All right. Come on. Should not be too much longer. Met.io, boost, and there's Trailing-Nos. Okay. And so now I can actually do Spack graph Trailing-Nos to see what that looks like, and it'll show me all the dependencies of Trailing-Nos that are installed with the same kind of ASCII art as before. So the graphing algorithm it's using is the same one that Git uses for the log view, or at least it's my interpretation of it. It's a little more compact, but not too much. So there you can see what Trailing-Nos depends on. All right. And you could install another version of Trailing-Nos with a different HDF5 and a different MPI if you wanted to. The same stuff works for even the bigger packages. Notice here, though, that the syntax is kind of nice because you don't have to know the dependency structure. You just have to know that it depends on MPI somehow. And so here you're saying, I want to depend on mpitch. And it ensures that the whole Trailing-Nos DAG is built consistently with that version of mpitch and that it coexists with the other ones that you have on your system. I'm not going to go through that, and I've shown the graph for Trailing-Nos. Okay, so here's a feature that someone asked for from EasyBuild. We actually do support uninstalling packages in Spack. And so I can run spack find -d libdwarf again, and it'll say, oh, there's 3 versions of that installed. And I can run spack find libelf. So we know what versions are installed of those things. You can use the same syntax as install pretty much to uninstall a version of some piece of software. So if I want to install the libelf that I've built with the Intel compiler at version, I think I did 15.0.6 and not 0.0.4, you can do that. And it says, okay, I'm going to uninstall that, yes or no, yes, and now it's gone. So you can uninstall that. If you tried to do that on a package that has dependencies, so for example, one of these libdwarf versions, let me go up here and find the libdwarf versions again. If I do this, let me try to uninstall this elfutils. So if I uninstall that, it's going to yell at me. It says, hey, this still depends on that, so you can't uninstall it right now. If I wanted to force it to, I can do that, but I might break a package. So it's going to say, okay, I'll uninstall it, and it successfully uninstalls elfutils. But now, Spack says, oh, well, your libdwarf is in bad shape. So if I do find -lm for show missing libdwarf, it should show me that one of these is actually missing. Okay, it's not showing that right now. I'll have to work on that. Spack tracks which packages have missing dependencies. So if you want to go and query for things that are missing one of their dependencies and it's no longer installed, you can do that. We reference count all the things that are installed. Yep.
Does Spack support installing stuff in different locations? I mean,
does Spack support installing stuff in totally different prefixes? Let's say some stuff in /opt, some stuff in /spack.
So you can change the install prefix to some extent. So if you go in here to the defaults, there's a config.yaml, and it looks like this. You can say where the install tree goes, but right now you can't change the layout of that.
Okay, but
right.
The reason I'm asking is removing packages. One of the reasons we don't have it in EasyBuild yet is because with EasyBuild you can easily install stuff in different locations, and as long as EasyBuild sees the modules in ModulePad, it's happy. When you want to remove something that's a dependency for other stuff, you have to be very sure that you're actually seeing all the modules and what they depend on. Because you may be removing a dependency and thinking it's safe, but it's actually dependency somewhere else and you're not taking that into account.
Well, so that's exactly the warning that Spack just spit out, right? So when I tried to uninstall it the first time, it said libdwarf depends on.
Yeah, it knows that. It knows that because that's one of the packages installed in its current installation prefix.
Yes.
What if I change the installation prefix, and can you have like mixed dependencies across prefixes?
You can't. So Spack manages one prefix that can have arbitrarily many packages under it.
Yeah.
You can change the prefix, but you'll get a completely different stack. We'll have one installation location right now.
Okay.
Yeah. So, and I could have multiple Spack instances, right, that are managing different prefixes.
How does that work if users are building stuff on top of things that are centrally installed? Because then you're effectively using two different prefixes.
So I mean, if users are, I guess I'm confused at the question.
Say sysadmins install software with Spack in the central location,
Sure.
/opt.
Mm-hmm.
A user wants to install stuff on top of that, also using Spack, but he doesn't have write permissions in /opt, so he builds in his home directory.
So right now we don't allow you to link an external dependency tree to your user install. It's separate.
You have to, the user has to start from scratch.
Yeah, but well, so not completely from scratch. You can have external packages, but you have to specify them one by one right now. So you could go and say, I want to use all these externals from an external Spack instance, but you can't point at the install prefix. It won't read an external database.
Okay.
That would actually not be that hard to add because we could just have.
Yeah, and then what happens if the sysadmin removes a dependency thinking it's safe because nothing is depending on it anymore in the central location?
Right.
But the user relies on it.
Then bad things happen.
Yeah, so that
I mean
that's one of the things I'm concerned about with EasyBuild, because it's so easy to just spread things around. If you're removing something, you're never really sure it's safe to remove it.
Well, yeah, I mean, anytime you allow uninstall, right? Once you've uninstalled something, people can't use it anymore. But you know, we do like to clean up the packages every once in a while. So we actually support it and we track the dependencies.
So removing package from the system, it's a nice way to notify the users that the package is removed, right?
Yeah. Okay. So I don't think I need to go through the uninstallation of Tralinos. We could do that too. I can show a little more stuff with Spack find. So at this point, if I type Spack find, I've installed quite a few things. So there's all of them with just 2 compilers because I installed that one libelf with the different Intel version. If I want to see just the stuff that is compiled with Intel, I can use an anonymous spec. I don't have to put the initial package name there, so I can just say %Intel. That's everything that was built with the Intel compiler at any version. And I can do the same thing for GCC and just show the GCC stuff. So I can use the same syntax for matching on the stuff that's installed. If I want to find the stuff that was built with a particular set of CPP flags, I can do that too. Spack find CPP flags equals -03, and it'll pull up the libelf install that I did with those flags. So that's tracked, and you can go and search for it again. And then finally, if you want to see where things live, you can say Spack find -p or -pe, and it will show you all of these different paths where the things actually live. And so you can see that they're all rooted under that opt Spack directory in the Spack installation tree. And so Spack has a lot of commands, and it has a lot of syntax. So we have some pretty good help for that. So if you say Spack-H, it gives you sort of an overview of the basic Spack commands. And so here's all of that. So, and they're divided up by querying, building, environment, and so on. If you want to see all the stuff that Spack offers, you can say Spack help -a like this. And that is a much longer list. So this is all the different subcommands of Spack. And there's stuff for administering, querying, building, configuring. There's developer packages or developer commands. We have like test things that you can run before you submit a pull request. It's very easy to add an extra command to Spack, so we have a lot of different things on the command line. And then if you need help on the syntax, you can say Spack help spec with 2 dashes, and it'll give you sort of a visual overview of how to do the different versions and version ranges and compiler modifications on the command line. And then examples of HDF5 down here. So this is kind of a cheat sheet for the syntax. So that's available. And then finally, I guess I can show this off. So if I type Spack compilers, it'll show you all the available compilers. And these are essentially things that it's found in my path. And if you want to customize that, then there's a YAML file. Let's see if I can find the, I'll do this myself. So there's a YAML file that gets installed in ~/.spack/ your platform, and it's called compilers.yaml. And if you look at this, it has all the metadata for the different compilers. So if the auto detection does not work for you, you can always go and customize this file. And if Spack doesn't know how to detect the compiler. You also have to customize this file if you want to do things like mixed compilers. So if you want to use, say, Clang with G4tran as your Fortran compiler, you would have to edit the file manually because we don't currently detect that. Yep.
Does it only look at path or Linux or anything else? Like,
We'll search.
figure out for modules.
It also searches modules. On Cray. Yeah, it searches modules on Cray. Not on Linux yet. That's true.
So it only checks modules on Cray for compilers.
At the moment, yeah.
Yeah.
All right. So there's that. And then just to demonstrate, I could remove this file, and I could say Spack compilers, and it would rerun the detection and find all the stuff in my path. So it's going to go and find those and search. And so this is fewer than I had before. Because not all of them were in my path. I had found them in other directories. But if I had a specific directory that I wanted to add a compiler from, I could say Spack compiler add path to compiler. And it would, if that's the prefix, it'll find it there. If it's the bin directory, it'll find the compiler. It'll auto-detect it based on just running the command and querying for the version. Okay, so that's the basic usage. Any other questions on that stuff before I move on? Yep.
Yeah, so for example, if you're installing several versions of the same software, it's more or less clear with the libraries, but what about if it is a binary? So if you want to use different versions of same application.
In the same environment, or, I mean?
Yeah, if you installed Spack, for example, I don't know, VI, for example, or WASP, several versions of WASP. So if I understand correctly, then path will be added automatically, or all these binaries will be in the path, right? So how I will run proper version? Or
so it's actually not adding them all to the path. So they're getting installed, but they haven't been added to the path yet. We generate modules for the things that are installed so that you can just load them. And then there's also a Spack load command. So you can type Spack load, say libelf, and that will put libelf in your path. And so libelf comes with like elf dump. So that's a binary. All of them have their own elf dump, and whichever one you load ends up in your path.
All right, yeah, clear. Then next question is about if I'm installing software centrally and I want my users to use this software, how do I do it?
So I'm not going to get to it today, but you can generate module hierarchies, and you can generate either flat modules or LMOD modules with Spack. And if you go over here to the module configuration tutorial, there's slides, and there's also a guide for we have a YAML syntax that you can use to customize the module naming scheme. And you can also do things like pick what things go in your module hierarchy. So you've seen like module hierarchies with compilers and with MPI implementations. You can also do module hierarchies with things like BLAS implementations in Spack. So you can use pretty much any virtual dependency, and I'll talk about what that is, to generate your hierarchy.
So if, for example, application like Gromax, which is usually compiled in serial and also in MPI to get there. So in Spark you have two module system for each version of it.
So I believe, and I'm not 100% sure about this, but that you can configure a module hierarchy where there's some stuff that just doesn't have MPI. I don't remember exactly how to do that off the top of my head, but I believe that's in the module tutorial. Okay, cool. So let's go back here. Okay. All right. So I guess I'm gonna log over here again. Okay. So I think if you think about the traditional package systems, they don't really support combinatorial versioning like this. We thought about using RPM and other types of packaging systems like that. And what ends up happening if you try to use RPM for something like this is you have to come up with a naming scheme, and you eventually run out of names because you haven't thought of all the variables that you wanted to build with. So like, for example, we can do different versions by compiler flag. You're probably not going to make an RPM that has all the compiler flags in the name. So if you think about what RPM, APT, all these other package managers are doing, I think the easiest way to think about them is they're get me the current version of this software sorts of systems. And you can have one version of that software installed. It's the one that comes with the system. And maybe there's different versions, but you would have to swap them in and out. Port systems like BSD ports and Mac ports and Homebrew are pretty similar in that regard. Homebrew has some support for multiple versions of things, but again, you have to swap those things in and out. You can't generate module hierarchies like you can with Spack or EasyBuild. And then others have asked, well, why don't you just use virtual machines and containers to do this stuff? Why don't you just provide containers for your users? And I say that, I think that's a good idea. I think you should do that, but someone has to build your container. And so, people have often said, okay, now that we have containers, we don't need to worry about package managers, we can just distribute these containers. But, someone still has to build the container. And I think package managers are really a really good complement to container systems. And so these things are complementary, not at odds with each other. These are just two different ways to, speed up your life. Containers are for deployment, and package management systems are for actually managing the software and for experimenting with new configurations that maybe you don't have ready in a container already. So how does Spack do this? What's really going on under the hood? If you think about what a dependency DAG looks like, here's one for the MPI leaks tool that I showed you in the slides before. What we're doing is we're considering each graph like this to be a unique configuration. And when I say each graph, I actually mean everything about the graph. So the nodes actually have metadata on them. What compiler were they built with? What version are they at? The build options, things like the variants. And then also the links have metadata on them. We can have different types of dependencies. So there are build dependencies and run dependencies. Anything about the graph that changes and you get a new hash. And when we install things in Spack, we install it into a directory that's identified by the hash. So the root of the DAG goes in its own directory with its hash, and that hash includes all the dependencies hashes, and the dependencies get their own prefixes and so on. And so essentially you end up with this layout of files in the file system that all know how to find their dependencies because we use RPaths, and we inject those into the build with compiler wrappers. And that's sort of hidden from the package author. We just do that automatically. For the most part. Some of the builds have to do some patching to get that to work. But the expectation is that once you install something with Spack, it will work because you RPathed it. And you don't have to tweak things like LD library path to get your package to run. And to be honest, I think that's the right way to do things in a multi-user environment like our HPC systems, because you really know what's going on with a package when you build it and when you install it. But by the time you get around to running it, it seems unreasonable to me to expect your user to know that this package was built with a particular version of MPI or a particular compiler. And so we embed that kind of stuff in the binary so that it just works the way that you built it. And you don't have to do things like set LD library path. Okay. And we talked about this a little bit, but this is what's going on when you constrain the dependencies. So when I say Spack install MPI leaks with the Intel compiler at 12.1, depends on libelf at 0812, I'm saying I know that that thing depends somehow on libelf. I don't care about the structure. I just want libelf to be at that version because I know, say, that the default version was causing me problems the last time I tried this. And so we have a syntax that lets you say that. The user is supposed to say what they want, and Spack just fills in the blanks. We support ABI incompatible interfaces like MPI. There's actually quite a few of these in Spack. We're calling these virtual dependencies. It's not 100% new concept. Systems like RPM and Debian support virtual dependencies. You can say that one package provides something, and another package depends on that something, which allows you to have multiple packages that can satisfy the same dependency. And so in our case, you can see that MPI leaks depends on MPI. And for MPI, MPI is not a package. OpenMPI is a package, and mpitch is a package. Those are implementations of MPI. MPI is really an interface, so we're modeling that in the dependency system. And you can use the same syntax to constrain a virtual dependency that you can a regular dependency in Spack. You just say caret, and then you put the implementation that you want. So that's what I was doing when I said install HDF5 with OpenMPI or install HDF5 with mpitch. This is the same kind of thing. Install MPI leaks with mbapitch at 1.9. Or I can install MPI leaks with OpenMPI at 1.4 or higher, whatever version of 1.4 or higher you have. One distinction between Spack and the virtual dependencies in things like Debian is that we actually version them. And so in the package file, I can say that mvapitch at 1.9 provides MPI at up to version 2. And so depending on the version of the package, you can provide different versions of the MPI interface. And so applications can depend on things like MPI at 2 or higher. And so they don't have to depend on a specific implementation of MPI or a specific list of implementations. They can just say what their requirement is, which is they need the MPI 2 interface, and you can satisfy that with any implementation of MPI that provides the MPI 2 interface. So that's all modeled in the dependency system, and Spack would let you experiment with that. It'll let you substitute in any MPI that provides that. Any questions about that? Nope. All right. So what happens when you say Spack install? Here's what you're providing to Spack. So if I say Spack install MPI leaks linked with the call path library at 1.0 plus debug, that's an option, with the libelf library at 0811. What Spack does is it builds up a partially constrained DAG. And so it puts those constraints on the DAG, and then we do a solve to fill in all the blanks and to pick versions and configurations of the other packages that will satisfy all the dependencies of this DAG. And we call that concretization. What we're doing right now is sort of a greedy solve that has been pretty good so far. But this is actually an NP-hard problem, and we are looking at replacing the current concretizer with a SAT solver so that we can do this properly and do more backtracking and try more things before we give up. And then, like I showed, you can store all the metadata once you're done. We store the full concrete metadata so that you could go and rebuild it again later, although we don't make that easy currently. If you want to see what Spack's going to do before you install something, you can use the Spack spec command. So you can say Spack spec and then MPI leaks. It'll show you the input spec, the sort of partially constrained DAG there, and then it'll show you the concretized version with all the blanks filled in. And so you can see what you're going to get before you actually install a thing. And then finally, I said that Spack installs everything in its own prefix, and that kind of goes against the installation model of interpreted languages like Python and Ruby and Perl, where the extension modules are sort of expected to be installed in the same prefix as the interpreter. So what we do right now is we do install all the extensions in their own prefix, and the packages actually declare themselves to extend, say, Python. And what that means is that we can actually symlink the extensions on demand into the interpreter prefix. So we sort of compromised, and we said, okay, we can install as many versions of these things as we want. We'll provide modules for them so you can load them and get them in your Python path. But if you do want some of them to just be available in the interpreter by default, you can do that, and we have a Spack activate command for that. So you can say Spack activate, say PyNumPy, and it'll take NumPy and link it into the Python interpreter directory so that it's available when the user launches a Python interpreter. That does modify the Python installation directory, and so we only allow you to activate one version of NumPy per interpreter at a time, but you can activate it and deactivate it, and you can keep swapping extensions in and out of the same interpreter directory, and it'll activate them with all their dependencies in there as well. Yep.
This requires the right access to the installation.
That's true.
Yeah, so this requires right access to the installation directory. So a user that uses software installed by an admin couldn't use Spack activate.
That's true.
I guess you could have a shadow directory or something where...
Well, so what we're thinking about adding is, I personally don't like this model as much. I think this is a decent compromise. It's our first crack at the implementation of this, but what we would like to have is environments sort of like Conda offers, where your user could just say, make me a new environment. And then they would say, put Python 2.7 in the environment and put these 5 extensions in the environment. And then they would just get linked into a common prefix in the user's home directory somewhere.
You do a symlink farm somewhere in home, or...
Sorry?
You would do a symlink farm somewhere in home.
Yeah.
Yeah.
Or, yeah, in a known location. Maybe they could do an arbitrary directory if they want to, something like that. We actually support that right now. There's a Spack view command that you can use to build up a common prefix and to just do symlink. You can symlink installed packages into a common prefix. It's not as easy as doing a Conda environment, but you can say Spack view create, make a directory that is the view, and you can say Spack view link spec of package into this view. And so you can build up a common prefix like that right now. And users can do that with system installed software if they want to. It's a little more cumbersome than environments.
Do you share the home directory across different platforms, different architectures? Using, for example, an any other Intel kind of environment?
So I mean, at Livermore, we do share the home directory.
Okay, because, well, if you take this way, and you use the home directory and it's shared across different architectures,
right?
You could have binary incompatibility.
So that's true. So there is no management of that right now in the way that we've implemented views. Like I said, it's bare bones. So we're not, say, making a view that's cross-platform. You'd have to build it up again for another architecture. If you'd have to build it up again on each machine that shares the home directory. So you'd have to make several views for that. We separate them in the install tree, as you saw, because the hashes are different and because the prefix inside the opt install directory is different. But yeah, we don't manage that for views right now.
Thank you.
Okay. All right, and I talked about that. I'm going to go through a few different features of Spack before I get to the packaging tutorial. We do support building against externally installed software, so you can depend on, say, your vendor MPI. This is one of the places where we differ from package managers like Nix and Geeks, which like to own the entire universe. Since Spack is for HPC machines, we do want to be able to depend on the system MPI, the system MKL, the system optimized versions of things. And so I'm not going to get into the details of it, but there's a packages.yaml file. And essentially what you do is you can edit that file and you can put a line in there that says, here's a spec. So this might be, this might be OpenMPI at 2.0.0 with a particular compiler. You provide as much information as you know about the package, and you put a colon there, and then you put the path to the package, and that's all you have to do. Once you do that, Spack knows at least some metadata about that package, and it knows where it lives. And it assumes that your externals are in a prefix. And then you can build against them like you would other packages. You can also say that they're not buildable, so if you do that, then Spack won't try to build that package. So here we're just setting up all the system open MPIs and saying that they're not buildable, which means that Spack will always use one of these. And what happens when we do that is if you provide an external package to Spack, we currently just cut off the dependency DAG underneath that package and assume that you're on your own if you're using that. And we hope that there aren't incompatibilities between that package and the rest of your DAG. We don't look at what it depends on right now. And so if you build with an external, you'll get a DAG that looks like the one on the right. As opposed to if Spack had built it, you would get all the dependencies of OpenMPI linked in that Spack built. Okay, Spack supports external package repositories. So if you have your own local packages that you also want to, that you don't want to release for one reason or another, and you don't want to push them into the Spack mainline, then you can do that. We let you create your own repo, so you can say Spack create path to some repo that creates a directory in the file system where you can put packages, and you can say Spack repo add that repo, and then it'll be registered with Spack, kind of like a yum channel. And then you can list what repos are available with Spack repo list. Most of the features in Spack have command line support like this. And what that says is that my repo is on top, so if you're searching for a package to install, it's going to pull first from your package. So if you say, install foo, and foo exists in my repo, it'll take that one. If foo doesn't exist in my repo, it'll look for foo in the built-in packages. And one cool thing about this is that your custom packages can depend on the Spack mainline packages. So you can say depends on MPI or depends on OpenMPI or HDF5 or whatever. And so you can have your packages coexist with what's in the Spack mainline very easily by just specifying the name. And you can compose those the same way that you would any other package. Okay. Finding source code, we do support mirroring. And actually, when you download source code from the internet, Spack caches it in a local directory. And you can take that directory and you can ship it over, say, to an air-gapped network. We need this at Livermore because we have a classified network, and so we have to ship entire applications over there to be built on the closed side. So essentially, for any package, you can say Spack mirror create that package. It'll build you a directory full of all the tarballs that you need to build that thing, and then you can ship it over to whatever non-internet connected network you have. And by default, if we've cached the package, we'll just fetch from there and then try the internet if it's not there. We're looking at setting up a global Spack mirror at Livermore. Maybe we would put it in like AWS in S3, so that if the download site goes down for a project, then you would still have it. We would just be hosting it for you. and that would, it would check there before it checked the internet. And then we already talked about adding custom compiler flags, but again, you can do this to do compiler flag studies. And I think this is part of how ARM does their compiler testing. They use Spack for their compiler regression test framework. Okay, any questions before I go on to making packages? Yep. Kenneth has a question. You should just sit next to Kenneth.
So maybe this is too early. Maybe we have to save this for the roundtable if you still have time for that. But so the whole flexibility that Spack has for juggling dependencies and compilers and auto-detecting compilers, it seems to me that that makes it harder for people to reuse each other's work. In the sense that with EasyBuild, at least in theory, if you use an easy config file that worked, if I give Pablo an easy config file that worked for me, he's reasonably sure it's going to work for him as well. If you install something with Spack on your Mac or whichever system you're on now, and I try the same command line, that's a whole different story.
Why is it a whole different story? So if you're using the same version of Spack and you type the same command line on the same platform, you'll get the same DAG. It's deterministic.
On the same platform, if
Yes.
I have the same compilers, I mean, there's a lot of ifs there.
That's true, but I don't see how EasyBuild is any different in that regard because you have to have the same compilers and the same easy configs in the same way.
Everything is version fixed, so that's how it's different.
That's true, but if I use the same command line, I'm providing the same constraints.
Yes, but it also depends on what's there already, I guess, or which compilers you're actually using. Using GCC 4 or 6 can have a big impact on both the result that you actually get and whether it's actually going to work or not.
So like I said, we do store the complete metadata, and so we're working on ways to actually dump that and give you a complete, concrete DAG to reproduce on another platform. So it's not like we can't do that.
And even with the stuff you dump now, so the YAML file you have in the install directory, the fully concretized thing, would that just work? So say if you're doing it on RHEL 7 and you give me that thing on Mac OS, it's not going to work out of the box because I don't have RHEL 7 on my Mac.
Well, so there's no reason that I can't go and take the platform descriptor out of that DAG and then try to build the same thing on Mac OS. And if Mac OS somehow conflicts with a build option that you used on RHEL, then it's going to yell at you about that, right?
Or maybe the compiler is just not available on my platform, so that's another level. I mean,
well, and so again, we could take out the compiler and we could build it with a different compiler, right? Like you can change the metadata in the DAG.
Yeah, this kind of comes back to my earlier comment in a comparison, EasyBuild versus Spack. That Spack is more, let me try to word it more carefully than I did before, it's more oriented towards software developers that want a lot of flexibility.
Sure.
While EasyBuild really focuses on support teams, and let's say reproducibility seems to me is more important in EasyBuild than it is in Spack.
So I don't actually think that you could do the reproducibility scenario in EasyBuild that you just described. Because A, you don't run on Mac OS, and B, like if you took the same easy configs, like they're tied to a platform too, right? So
we try very hard not to, because that's why we take control over compiler MPI. That's why we start from the ground up. And
So I mean, the difference is that we let you have the flexibility up front. We do arrive at a concrete package spec though, right? So we have all the metadata that you need to reproduce some fraction of those things. What we don't have right now is an easy way to dump it out and say, here's a package to reproduce this stack. And what we'd like to have is an archive that has all the tarballs, all the the YAML files that you need to go and rebuild a thing. And then the other sort of interesting thing that we can do, because we have all the metadata, is you could have a syntax that says, look, I want to build this again, but with this other compiler, right? We could tweak little parts of the DAG, and we have a syntax that lets you do it.
Sure.
Yeah.
What's the main reason that's not there yet? I guess time is a factor, but
so we just have a bunch of other priorities. Yeah. I mean, and I think
so. That's again sort of my point. I mean, it's not a big focus for Spack. Otherwise, it would have been there already.
So we have a working group on environments right now, right? So we are working on it. I don't know what I can say besides.
Reproducibility is part of that, of the Spack environments.
Yes.
Okay.
So the environment would be something you could dump and then reproduce somewhere else.
Okay.
Yeah. All right. Okay, so for making Spack packages, I'm going to go back to the tutorial here. Oh, do I need to change something? No. Okay. If you go to the package creation tutorial here, we're going to go back to the Spack install. I have a ready-made Spack package directory with some dependencies of what I'm going to show you how to build. So if I go into opt, I can just blow away my previous Spack data, and I can move the demo into place. And so now if I say Spack find, I've got the dependencies of what I want to show you how to build. So to create a Spack package, we're going to use Spack create. And essentially, Spack create, all it requires is a URL. So if you have a URL for a package, and it's a well-formed URL that has a version and a name in it, which most distribution tarballs do, then you can start to create a Spack package by just saying Spack create URL. For this demo, I'm going to say create-f because this package actually already exists in Spack, so I'm just going to overwrite the one that I already have. That just says overwrite it if it's already there. So what it'll do is it'll say, oh, this looks like a URL for MPI leaks. I found one version of that online. It goes and scrapes the web page and says, hey, there's a version available for that. And it says, how many of those do you want to checksum? There's only one here. I guess we could make it automatically do it if there's only one. And then you get boilerplate like this. And why is this not working quite the way that I want it to? Let's see. So the only problem is I'm in Vim. Hold on a second. Oh, right. Let me get on develop. Great. Let me try that again. We'll do this. Nope. Not supposed to type Q. There it is. Okay. It'll download the tarball, it'll checksum it, and it'll generate me a boilerplate package that looks like this. There's a bunch of copyright stuff at the top, and then some instructions. And so it says this is a template file for Spack, and we put fix me next to all the things that you want to change. And if you want to try installing this thing, you can say Spack install MPI leaks like we've already demoed. And then if you want to edit this again, you can say Spack edit MPI leaks to get back to this package. So remember, there's only one there's only one package file per package. It's not like Easy Build where there's lots of configs. There's just this one template. And this is the thing that builds all the different versions. So once you've done this, you can look at this and you can see that the Spack package is basically, there's a from Spack import star at the top, and there's an MPI leaks class in here. Spack detected that this is an AutoTools package, and so it made it extend AutoTools package here. It looked inside the tarball to see what the build system was to do that. There's a doc string here. This is what we use for info. And then there's a home page and a URL. These are all metadata. So the first thing I'm going to do is I'm going to go through here and just say, here's a description. So this is a tool for finding handle leaks in MPI programs. And then you can put the URL for the package there. So I'm going to go down here and grab the right URL for this particular package. So let's do this. And once I've done that, this is actually in the Spack package repo, so I can just say Spack info MPI leaks and get info on the package. And so it says, there's my doc string. It goes in the description. There's a home page. It's already there. It knows the tarball, and you can see here that it figured out the checksum automatically and stuck it in the package for you, so you don't have to go and do that. So the next thing to do, or I'll just demonstrate this right now. Right now we can try to install the thing. So we can just say Spack install MPI leaks again. And it'll go and try to install with the package, but it's going to break because the package isn't complete yet. So it's going to go through here, and then it shows you where in the Python code it broke. And it says, hey, this build failed. Here's the build output. So if you want to see what happened, you can just cat that build log. We should probably just show that automatically. And you can see that, OK, it got this far through configure, and then it said, oh, I couldn't find a dept utils. So the reason for that is because it depends on that package. And so that's where we add dependencies. So in here, it says fix me, add dependencies if required. So we're going to go through here, and this particular package depends on 3 things. It depends on MPI, it depends on adeptutils, and it depends on the call path library. And you saw that from the DAG that I showed earlier. So if I want to make a package, I can just basically add those dependencies like this. And now I've got 3 dependencies for this package. And if I try to build again, let's see what happens. So Spack install, MPI leaks. What's going to happen? So it's going to recursively try to install all those dependencies. And I've already got them installed. So see up here it says it's already installed in this location. It's already installed call path, and it's already installed the dept-utils. I built those in advance for the tutorial. And then it fails with the same error. So if we look at the build output again, it says, oh, I'm unable to locate the dept-utils installation. Okay, so it's fairly obvious that the reason that that failed is because we didn't provide the configure arguments for it. But I'm going to show you what you can do if you just want to debug a package. So Spack builds in its own special build environment. And if you want to debug that, then you can actually get into the build environment by saying Spack env MPI leaks, and you can just say bash. And so if you do this, it goes and it sets up the build environment like it would for a Spack build of this package, and it runs bash in that environment. And so now, this is maybe more detailed than people care about, but you can type env grep Spack, and you can see all the custom Spack variables that got set up for the build environment. And you can say Spack cd MPI leaks. And this will take you to the build directory where MPI leaks is currently staged. So it downloaded the source and expanded it. And from here, you could try just running the configure script yourself. So you can say configure and run it and get the same error. And so yeah, there. So I got the same error that Spack did because I'm in the same environment with all the build stuff. Okay. So the final thing that you have to do to get this package working would be to provide some arguments to configure. And so if we go over here, I just done this debugging package builds part. I did Spack env and specifying configure arguments. It turns out it needs these arguments. So I can get back into, so to get back into the editor, you can just say Spack edit MPI leaks. It'll take you to the package file. This is something we stole from Homebrew. I'm going to get rid of all the boilerplate comments at the beginning to make this clearer for the demo. And once you've done this, you can just add the arguments. And so it needs with adeptutils equals the prefix of the adeptutils dependency, and with call path equals the prefix of the call path dependency. And then we just return those arguments. And make this a little clearer to see. So one thing you can see here is that to get the prefix of your dependencies, you're just saying self.spec. That's the DAG. So the spec is actually a descriptor for the whole DAG. And you just say the name of the dependency that you want to refer to. So spec sub adeptutils is the sub DAG for adeptutils. And likewise, spec sub call path is the sub DAG for the call path dependency. And so if you just say .prefix on that, that's the install directory for your dependency. And so if the build requires this sort of thing as a parameter, then you can get at it very easily from here. So now given that, I've got the whole package set up. I can say Spack install MPI leaks again.
Todd?
Yep.
Small question. Why isn't it finding the dependencies? Is that because the configure script of MPI leaks kind of sucks?
Yeah.
Yeah.
So for the most part,
because it's in the environment, right? Spack set up the environment because you've specified the dependencies.
Yeah, so it actually even passes them on the command line for the compiler. So this particular build, it's a CMake build, so it's searching for, it requires the parameter, or no, it's an AutoTools build. So I don't know, the MPI leaks build is not that great. It's trying to find a file in the prefix. It's not just testing to see if it can include the header. And so it's failing. So it relies strictly on the parameter. For most builds, you don't have to do this, but it's a good one for a demo because we can do broken builds. And so there. So now it successfully installed, it ran, it found what it needed to, and we're done with MPI leaks. So there's that. So here's MPI leaks. Let me check out one branch because I want to, yeah.
Todd, another question.
Yeah.
does Spack support resuming a previously half-broken installation? So
Yeah,
say you do configure build, it breaks in build, you change something, can you continue from that point on, or do you have to restart?
We continued from that point on here. So essentially, the configure got to where it couldn't find the adeptutils prefix, and then it failed. We didn't restage.
Are you concerned about people doing this in a staged way and then not redoing the whole process, because you have to make sure it actually runs through the whole thing without
That's true.
making any manual changes?
So right now, if the build fails, we just leave the build directory there because we're assuming that you're going to debug it.
Yeah.
And yes, you probably want to not package something up or deploy it if you built it that way.
Yeah,
Right?
okay.
You would want to restart the thing.
Yeah.
But we can uninstall it once it's installed and reinstall it again. Or there's also Spack clean, which will just blow away the build directory. All right. So the last thing that you might want to do with a package is you may want to add some options to it. So I showed that there were these build options, we call them variants, earlier. And so we can add a variant to MPI leaks. It turns out that MPI leaks has a build parameter called stack start. MPI leaks records the call path of where an MPI handle was created, and that's how it tells the programmer which handles are leaking. And you can tell it to trim off some of the stack frames on the call path by default. And so this is like an integer parameter that we can pass to MPI leaks. So if we want to do that, we can go back into the package here, and it doesn't really matter where you put the directive, but you can just say variant like this, and we'll call this stack start like so. And then we'll say the default is 0, and the values that are possible are integers, and the description of this option is, let's see, number of frames to trim, or something like that. So now this changes what the spec would look like for this package. So now we've added another parameter, and so when we generate that YAML, and when we hash the YAML to get the build hash, there's another piece of metadata on this node. And that's what this stack start parameter is. So for any value of stack start, we can make a new version of MPI leaks because it's now included in the hash. And to use that, you can just refer to it down here in the configure arguments. So if I want to access that particular variance value, I can say stack start equals self dot spec. So that's the DAG again. And I can say variance is a dictionary of all the variants. And then I can refer to it by name. So I can grab it with stack start like this, and I can grab the value of it. And since it needs to be an integer and we store them as strings, I have to do this. So I have to make it an int, which is somewhat tedious. We could probably get around that and make them the proper type by default, but that's what we have right now. And if it's not 0, then I can just append it to the arguments. And I can say with stack start C equals %s mod. And so this is just adding another configure argument. And I need to add it twice because there's a separate one for Fortran. Because you may want to pull off more frames on Fortran stack traces than on C ones. So then we're done with this, and now I can say Spack install MPI leaks with stack start equal to, say, 4. And remember, we already installed MPI leaks once, and so it's going to go and concretize this, and this will be a different version. So let's do the configure. We're going to build, and then finally we're going to install, and we get another version. And so if I do Spack find dash v d MPI leaks, then I can see what I installed. And so there's 2 versions of MPI leaks with all their dependencies. Notice that they're fairly complicated. And you can see that this MPI leaks was built without any particular options, but that this one has stack start equals to 4, because that's after I added the variant to the package. And so now I can parameterize my builds however I want. We use this for things like boxlib and other packages that require, say, a hard-coded dimensionality or some other build option. So you can build a 2D version of boxlib and a 3D version of boxlib, and they can coexist very easily by just adding a parameter. Okay. The spec object is actually kind of versatile. This is the last thing I'll cover. But from within the package, you can essentially just query that thing to figure out what you're supposed to do. So if you recall from the slides, what Spack is really doing is it's doing the concretization for you. So it takes this sort of weakly constrained DAG and it fills in all the blanks. And then by the time you get into that install method, you're guaranteed that all the parameters are set to something. And so that's actually nice for the package author because essentially it reduces the package author's task to translating a configuration into build options as opposed to having to do searches or figuring out what versions are installed on the system. You just have all that information in the spec. And so you can query that. So you can say, if I'm at version 1.1 or higher, then do something for that version. So it's very easy to put in conditional logic. Or if I'm built with OpenMPI, I can say if self-spec MPI.name is OpenMPI, I can do things with OpenMPI. I can test, what compiler was I built with. I can say if my spec satisfies %GCC at up to 5, and this is essentially the same syntax that I would use on a command line. I can test variance if debug is enabled, or if some dependency, so spec subdynance satisfies 8.0 or higher. And I could use a caret syntax for that as well. Basically, you can query anything about the DAG from within the package, and you could build differently. So if you have to do something different for, say, OpenMPI or MPitch, then you can test that and adapt to it. Or if you have to do something different if you're built with earlier versions of Boost, then you could choose to add a patch for that version. And actually, we have a patch directive that lets you conditionally do a patch with these kinds of conditionals. So it's very easy to specify that kind of stuff. Any questions about that? Okay, so I'll go back to the slides, and then I'm almost done. So I think the last thing I wanted to show you is Spack actually builds every package in its own compilation environment. And so this is how we try to make it very easy to write the packages and very easy to find the right dependencies when you're building the package. And so that was that environment that I popped into. And you saw all the Spack environment variables that got set. What's really going on there is every build that Spack does, it executes in a forked process with its own environment. And that's so that the builds can pretty much do anything to the environment that they want. They can't hurt the Spack core. They're off in a forked process, and so they can set environment variables like you would in a shell script. The other thing that we do there is we set variables like CC, CXX, FC, and F77 to our own custom compiler wrappers. And so we get in between the build system and the compiler, and that's how we do things like inject compiler flags. So when I said build with these other flags, we're actually injecting them with these compiler wrappers. And we set some other environment variables to the real compiler, which the wrappers end up invoking after they add some things to the command line. It's not just where we inject the flags. We also set things like includes, we set library search paths, and then the last thing that we set are R paths. And so this is how we ensure that the binaries that Spack makes know where the dependencies are. And so essentially you fork this process. You're running this other build process with a special environment that the compiler wrappers understand. When you run install, you're in that environment. We also set things like CMake prefix path and other things to help you find your dependencies. And then when configure is invoked, it ends up hitting the compiler wrappers, which invoke the real compilers. And then make and make install do the same if they run compilers. And then we're done. So for most AutoTools builds, and this is kind of related to the question that Kenneth was asking earlier, you don't have to do much of anything to add configure arguments for your dependencies. It just looks like to the package that its dependencies are on the system because we add the search paths on the command line. So you can compile most things with just a configure, make, install. But then obviously we let you do special things for builds where they don't find their dependencies in smart ways. So Spack will also do things like extrapolate URLs. So you saw this a little bit with the website scraping that we did. But this package specifies one URL, a bunch of different versions, and each version only has a checksum. Spack knows how to extrapolate some URLs and to substitute different versions into them. So it just assumes that the other versions of that package are installed in the same directory. That's kind of nice. It makes it easy to maintain the package files because people just submit new checksums with different versions, and we don't have to update the URL all the time. If Spack can't extrapolate the URL, you can specify a URL per version. There's some packages that just have bad naming schemes, and we can't do much about that. We talked about variants. We talked about build recipes, and we did the hands-on stuff. So the final couple things that I wanted to talk about are, I'm not going to cover this today, but you can configure Spack to automatically generate modules. And we can do both hierarchical modules and we can do flat module hierarchies. And there's a YAML file that lets you configure that. This is contributed by by Massimiliano Culpo at EPFL. And they use this at EPFL. At least they use the flat modules. And he also added the Lua modules. One kind of cool thing with that is, like I said earlier, you can take any virtual dependency, not just MPI. You could take different versions of BLAS, different versions of LAPACK, and you could generate a module hierarchy from those. And so you could have your user choose a compiler in MPI and maybe a BLAS, or a compiler in an MPI and a LAPACK, and you could have those stacks separate in your module hierarchy using our module generation. There's other stuff that you can do. You can remove the hashes from the modules that you generate if you don't want that on there for the users. And you can put suffixes and whitelist and blacklist different modules. So there's a fairly fleshed out set of configuration options for generating modules. Yeah, and see the doc site for more on that. It's in the full tutorial. Things that we're working on, we would really like to have environments, not just because, not just for reproducibility, but also because I think it's an easy way, and it's a way that people are used to using packages. I'd like to have this because there's not a lot of Mac OS systems that have modules installed by default, or that's like the usual usage mode for a Mac. And I think people are getting more used to Conda and virtualenv and some of these other mechanisms from other package managers, so we'd like to support something like that for Spack. The way that it would probably look is that you would get a virtualenv for not just Python stuff, but for anything. And as you Spack install things in it, you build up a stack. And we could say export that environment and then go and rebuild it on another system. And so we're hoping that that will help people with the reproducibility aspect, because we don't have that automated in the way that we'd like yet. We're working on secure binary packaging with CERN. They've actually already implemented binary packaging, but they didn't provide us with something that had signed binaries, so we haven't deployed that yet, because I don't want to deploy insecure binary packaging, but we're hoping to have that by September or so. And then finally, we're working on a better concretizer. So like I said, the algorithm that we use right now is greedy, but it's actually an NP-hard problem, and so we'd like to have a full stat solver in there so that we could do things like try to reuse more dependencies. This is actually something that you need a better solver for, is if you don't want to rebuild the same stack from the packages every time, you want to look at what's already installed and try to use those as aggressively as possible. It'll let us do a lot more things with the dependency resolution. We would probably continue to provide a more deterministic option, which is basically what we do now, where you get the same DAG for the same command. If we add something where we do a solve, then you're going to, it sort of depends on the state of the things that you have installed, which a lot of the users want, but it's not deterministic. And so this is actually a debate that happens in other package management systems. Like if you look at NPM and Yarn, NPM's a JavaScript package manager. It had sort of an install order dependent resolution mechanism that the users ended up not liking in some cases. Some users liked it, some didn't. And Facebook came out with Yarn, which does deterministic dependency resolution. And so now both are integrated into NPM, and you can choose between them. So we would probably go with a model like that. All right, so that's it.
Question on the roadmap. Are these 3 points, do you consider them necessary to have a Spack 1.0?
I would, so the binary packaging, not really, and the environment's not really. For 1.0, I want to have the new concretizer, and I want to have, I guess I should have put testing on here. So right now we have a lot of unit tests. We have like 700 unit tests that we run on every pull request on GitHub, but they're only unit testing the core. And we're working on setting up CI so that when you submit a package, dependencies of that package get tested automatically in the cloud in AWS. And so we would do tests like that for different OSs for every PR. And I think that would make the stack a lot more stable than it is right now. And we'd like to run that at places like NERSC on the Cray systems and also on BlueJeans and other types of architectures so that every request gets tested like that. So yeah, testing and concretization are probably the things that I would want for 1.0.
And what kind of timeline do you have in mind for that?
Well, I'm hoping to have both of those done by September. So we'll see how the baby in July affects that.
Okay.
Yeah. But it's not just me working on that stuff, so it may still happen, hopefully. All right, so if you're interested in Spack, again, go to the GitHub site, join the GitHub site. We're on Twitter. We're SpackPM on Twitter. The Spack account would just not listen to me. They really wanted that name. And definitely we would like more contributors and to broaden the community for Spack, because I think, you know, this would not be possible without all the people who are helping out. Like, you know, we're merging 20 to 50 PRs a week right now, and that's, you know, that's way more productivity than we would have alone. So we're very much supportive of open source. So thanks.
Thank you so much.
Any questions? Or do we want to do roundtable?
So do you have it in production or on production systems?
We do use, so we use Spack-generated RPMs in production at Livermore, and we have Spack-installed packages. We have a Spack install that's globally accessible that's in production at Livermore. EPFL and Argonne both use it in production. EPFL freezes their Spack version, and they basically just, they run off of that one. They only backport the patches that they need, and then they'll upgrade the whole thing, kind of like how EasyBuild manages their releases. And Argonne actually runs off of develop all the time.
More questions? Otherwise, we can raise those questions during the roundtable if you like. So we can run a short one.
Okay.
So John, do you want to join? Thank you.
Oh. You get to sit with the robot.
Should I sit here to keep it safe?
The robot's going to be like that. Also, maybe contrary to popular belief, we actually do like each other.
Well, we collaborate on some of this stuff, right?
Yeah.
I mean, Todd helped out with some of the RPod support we have in EasyBuild. We have a lot of discussions. And he likes to come to Belgium to have good beer, so.
Yeah, Belgium has good beer. So question?
So, well, reproducibility. This is an open question, right? So, if you try to build something with EasyBuild or Spack, you rely on the main developers of the software to still publish the source code and that kind of things. So usually, if you try to do that for all the packages that you have already installed, sometimes, you know, there are humans behind that thing, and sometimes they change their mind, and they decide to change the path of their URL. So it's quite complicated sometimes to even download the source code of some packages. We found that thing a few times now. And so there are some packages, I can tell you the names of the packages if you like offline as well.
I think MVA page is an example.
Yes.
Or at least it used to be an example, because we convinced them to not throw away all the releases.
Okay, that's a good thing. Yeah. So well, it's a risk on reproducing the whole thing. Building from scratch, it allows you to go further, to reuse the work and to increase the set of applications that you have there. But if you want a particular build and you want to archive it and you want to be able to run the same thing in a different environment, compatible platform, obviously, probably it's worth it to explore other options like Singularity, Docker container, or even virtualization. I don't know. So I know that, well, you're still running the BlueGen, so if someone wants to run the same simulation that they have already run on the BlueGen in 2 years' time, probably it's going to be quite complicated to do so. But for those that are more in Intel-like platform, there's still a chance for that. So what's your opinion on that?
That's a lot of stuff. So, I mean, what's my opinion on reproducibility for HPC? So a lot of HPC stuff doesn't rely on completely open source packages, right? So to some extent, you know, we rely on the vendor MPI all the time. And I don't think you're going to be able to get the same degree of reproducibility in HPC, if you want to keep the performance in it that you do for, say, an open Linux distro, right? So I have a keynote that I gave for a workshop at IPDPS a couple weeks ago on this, but I argued that, I think there's different levels of reproducibility, right? Like if you look at what we're doing in Spack, we could store the string that the user provides. It's essentially the constraints on what they want in the package. They're saying, I want this package at this version with these options, right? That's effectively their requirements. We could store that and we could reproduce a build as long as it satisfies those requirements, right? And you could extend that to say, we could reproduce it with the same compiler it was built with on another platform, or we could reproduce it with a slightly different version of the same compiler or something like that, as long as it satisfies those constraints. So I think you have to specify what you want to reproduce. And I guess, there's a whole reproducible builds movement out there in like the Debian community. I don't know if you've seen this, but they want anyone to be able to build the authoritative version of a package from source at any time, which means that they've made all their builds deterministic. And so if you build a Debian package anywhere, you get the same hash. But that completely precludes the ability to optimize for a particular architecture. They're giving you generic lowest common denominator x86 64 code, and they're not giving you the kind of optimized binaries that we care about for HPC. So I think if you're talking about reproducibility for HPC, across architectures, right, for a non-identical machine, you do have to relax some of your constraints for reproducibility. It's just, there's no other way around it. But I do think you should use containers if you want to reproduce on the same architecture. But even those are not perfect, right? They rely on the kernel interface, and so your kernel can age, and then your container won't run anymore either. So I think trying to specify what it is that you want to reproduce, and then focusing on that and making sure that that's accurate in testing is probably the way to go, if I had to pick.
Yeah, I think I mostly agree on that, and I would definitely, if your main concern is reproducibility, take a look at Singularity in HPC, because the Singularity developer, one of his selling stories is they had a desktop underneath a desk somewhere that was running Red Hat 2 or whatever. And the scientists were getting concerned, like the hardware is going to die because this thing has been running for 15 years and we still need this stuff. So what do we do? What he ended up doing with Singularity is creating a tarball, putting it in a Singularity container, and it still runs.
Yeah.
So
and that's fine if all you care about is Linux, right? And then, at Livermore, we're going to have a power machine soon, and that's different, right? Like, you can't take a container that was built on an Intel machine and run it on the PowerPC 64 machine.
No.
And so we would have to build 2 images of a thing or something like that. But we would still use images because it's easy. We care about things like disaster recovery. So like if something happens to Livermore and we still want to run our codes, we want to be able to run them at, say, Los Alamos, because we run there as well. I think Singularity is a really great tool for that kind of use case. We could have container images of all our application builds, and then people could reproduce the same simulation in another lab. Yep. I think that would be awesome.
If you look at the binaries provided by Intel, all the tool chain, it runs with and without instruction sets, so to speak. So you are able to run on any single Intel compatible platform. So this is the kind of mindset that I was looking for. So if you are able to compile that thing in a platform, I would say Haswell, Skylake, or whatever. So you can generate this container or this piece of software. It's containing an image, and then you can distribute that thing if you like. If you need, if the user or the researcher need to do that thing to prove that the research that he or she have done have a value. I think it's worth it.
There's two sides to that aspect. You could either package the existing installation and make sure it lives on.
Yeah, you need to support everything, but what you have done during your research, maybe it's of interest.
Regarding the reproducibility that Jordi was mentioning, I want to go to a lower level. This is something that we've been doing with Kim at BSc. we ran climate models, and at some point we realized that due to not using the appropriate flags, results were not reproducible on the different platforms. So, which is your approach on this? Because there are many codes that do not have tests. So you can not validate that the results are okay. The only way to validate as you were saying, maybe it's checking for the help, but if anyone is providing a recipe for this software, how do you ensure that the results that you are going to get in the different platforms are reproducible?
You should if you install software, you should always check what it's doing, and if it's spitting out, first of all, results that look reasonable, and maybe have results that you can compare it. I mean, with VASP, for example, we had an issue that, yeah, I mean, we installed it for users, and they come back to us and say it's just spitting out bullshit. The results don't even make sense in a physical sense. The physics just don't add up. And it turned out that it was being optimized for the architecture it was running on, which was breaking VASP somehow. I don't know what it was. When using AVX instructions, it stopped making sense.
Well, in that case, the results were making sense. So it just that the simulated climate was different.
It could be a problem with the installation. It could be a problem with the software itself.
Exactly. And also, it could be problem dependent. So I mean, you could have something that's reproducible on one problem and not another.
No.
I guess I mean, if you're talking about optimization flags, right? Like if the code's not robust to the optimization flags, then you probably shouldn't build with the optimization flags, right? And in which case you could just build a x86 64, no vector, no special optimization version of the thing and sacrifice performance for reproducibility, right? And what you have there is like the application developers have to go back and figure out what's wrong with their numerics. I mean, at some level, there's nothing you can do about that.
Exactly, but I mean, how do you plan to deal with this? Because you have people contributing, and how do you ensure that what they provide is okay?
So, at least in Spack, we have another project called SWL at Livermore that focuses on running and testing the actual binaries, and so we use that for our acceptance tests for our hardware. That's also a Python framework, and so one of the things we were thinking about doing is just adding some methods to Spack packages to allow them to run either the smoke tests or the exhaustive tests for the application.
Is that available?
It's not available, so that's not something we've done yet. But that's the plan. There's a lot of abstracting of, like we were talking about the other day, of some tests like to run in the source directory, some like to run in the install directory. I'd like to generify that and just have one interface so you can say test that package. And you could either do the long test or the smoke test, or maybe have a continuum of tests or something. But I think ultimately the tests need to be written by the application developer, right? I don't think we as packagers cannot write a test suite for a major physics code. I think the best that you can do is provide a good interface to it so that there is an API for testing something installed with your tool, and then automate that and verify it as many ways as you can.
And I think that's like the next frontier. We're now looking into collaborating on getting software installed, because it's just a lot of work and it makes sense to collaborate on it. Sort of. Well, yeah, there's 2 groups now. But like the next big thing we're going to have to look into is testing and validating software. Not only that it works functionally, but it spits out stuff that makes sense.
I will point out that one reason that we designed Spack the way that we did, so that it's flexible, is so that we could test a lot of different configurations in a scenario like this. Whereas like with Easy Build, you can only build a config that someone's already written. We can go and generate all the different combinations of ways to build a package and sample that. And we could say, we could do the application test suite, but we could do it in some representative sample of configurations. And that might be a way that we can validate codes in the future, and our model supports that. So you can build something that you haven't built before.
Okay, I can agree with you that the problem is on the developer side. I mean, not everybody is Gaussian that provides you with 1,100 tests that you need 1 week to run with a couple of servers. But it's also true that, for example, a problem I found with VASP or Siesta is that depending on the set you are using, I mean, you can be well, you can use O3, so this will be really fast, but then the scientific results won't have any sense. So it's a matter of I mean, you have to see, you have to deal, you both, in I want the final binary to be really fast, because it's important also the performance. I mean, sometimes, especially in Siesta, we've seen that there is just one option. I mean, dealing with the compiling flags, the results vary 50% on the performance, but only one was the real one that had scientific sense. So I mean, for the future, you also have to be there. I mean, of course it's on their side, but also you, because you have many options, and the developer is not always telling you which is the right one, because it depends, of course.
Well,
I mean,
so I think you need to separate the concerns, though, right? So
sure,
the application developer has. I don't have the knowledge to write a test suite for a multiphysics application, but what I can do is switch out the compiler flags in lots of different ways and tell them if their test suite is saying that the code is valid in different configurations, right? So I can give them an idea of, you know, the flag coverage that their test suite has by swapping out the flags and saying, here's the configurations where your test failed, and here's the configurations that didn't break your test. What does that tell you about your numerics? And then it's, you know, up to them to release a new version.
Yeah, of course it's on their side. What I mean is that it's really helpful your software, but it's really important. I mean, there's a lot of manual work on our side, let's say, in the Islamic side, because you want to test that the results are good, and finally, and especially the performance are good.
Right.
So I mean, not for now, but in a few years, we expect to have this in the other side.
There's a next frontier. There's something in between.
Yeah, that's it. I mean,
and one of the things as well is the domain experts really have to come up with the tests, because we just don't know the software. We don't have the expertise.
yeah.
But that's not enough. I mean, you can have a software package that has 1,000 tests in a proper test suite. That doesn't mean people like us can actually validate the software.
No, sure, it's not.
Or that it has.
So we will need to work with domain experts very closely to actually make that work well. Because verifying results, especially when you're doing the numerical differences, I mean, when is it good enough? Yeah.
What I mean, the bad news for the supercomputing centers is that they cannot rely, they never will be able to rely on Spack or easy build. I mean, because you always have to take care with this, of course. I mean, well, you know better than me, but.
Well, we could, I mean, you could, I guess what I'd say is, like, we're both trying to automate this process, right? Yeah. Like, and actually, like, you're talking about a regime where the amount of work that you have to do it's a huge amount of cycles, right? And, you know, a Spack or easy build release could be backed by that kind of testing, right? Like, that's sort of a release management question. Like, right now, we're in the early days for Spack, but you could imagine, like, 5 years down the road that, you know, for certain packages, we certify them as having been tested for, like, 1,000 different compiler configurations with their long test suite. And maybe, you know, someone could figure out how to pay for those cycles. I think that's another question for the facilities, because right now, if you look, we're talking about implementing continuous integration for the US ECP, the Exascale project. I'm leading a group that's trying to deploy that. And it's one of the tougher things to do beyond just the technical challenges of running CI at an HPC center and all the security challenges is convincing the centers that testing cycles are valuable. And because they're like, well, we already have these projects paying for production cycles. And I'm like, well, what good are your production cycles if they're all wrong? So, you know, how valuable are the test cycles to you? And I think the centers view it as, oh, these application developers are going to want more cycles, but I sort of think the application developers and the centers need to think about that, and maybe the application developers should devote more of their production cycles to testing. You know, maybe that would be something that they could do that would help their results.
It's partially up to the users as well.
Yeah.
I mean, we always tell the users, check what we installed for you. Make sure it works. Not everybody's able to do that or maybe willing to do that, but we've had issues that people start using the installations just blindly, and then after 3 months they come back and say, hey, the results look a little bit weird. What's going on? I said, did you actually verify the very start? No, we just started the project and wasted 1,000 years of compute time.
Just another question. Similarly to what you do with hierarchical modules, do you plan to add, for example, the detection of the microarchitecture in which you are going to run? for example, detecting if it's EV bridge or Sandy bridge or Skylake, so that you have the most performant binary for the architecture you are going to run?
For EasyBuild, we're just relying on the compiler to do that for us. We're
Yeah,
just telling the compiler -x host for Intel, for example, optimize for the architecture you're building on.
So for Spack, we have some work in progress that detects the architecture, and we could store flags based on the architecture name if we have better ones than, say, the compiler does with -fast.
So well, this is from HPC now. What we are doing, it's using the output of LS CPU, which provides a next decimal format for each CPU kind, and then we build with EasyBuild applications in a different folder based on the hash that we got.
Yeah.
So it's a nice way to share the applications on the same platform and same architecture.
We do something similar in Gantt. Yeah, basically we install the software again if it's a different platform, but it's just not automated.
Sorry, I have been around here. So more questions over here? So otherwise, we can close that.
Maybe a question for the people here that are already using EasyBuild or Spack. What's the biggest thing that they are missing?
Oh, come on. Let's just start the competition. Come on.
Are people missing
yes,
something?
No. It's okay. It's okay. But I think that it's fair to say that before there were more people before.
Yeah.
And so take into account that thing.
No, I'm just
no,
saying
yet.
whether they're using Spack or EasyBuild, it doesn't matter. What is missing
I misunderstand that.
in tools like this? So I guess the testing thing is part of it, but is there anything else we're just maybe overlooking, or
Some magic, maybe?
magic?
Yeah, you thought that there is no magic, maybe. So
There's a little bit of magic.
More
magic.
to compensate for bad configuration scripts, etc., that are provided along with software. I'm just kidding, but yeah, that's the same way though.
Are you saying we should be in closer touch with the application developers?
Well,
Like report back all the crap we run into?
well,
I don't think that's a bad idea. I think
It's
actually
a very good idea, but have you tried it?
We do report back to our application developers locally. Yeah.
Yeah, but that's
Yeah. I mean, we have a lot of them. So.
just to. We've tried it before, and sometimes you just say, whatever. Intel compilers, we don't care about Intel compilers.
Well, I mean, so I guess I would say that I don't think there's magic, but I think you can automate a lot more stuff than you automate today. And there's a lot of wins to be had there. Because, I mean, we've talked about taking like all the applications that we have in Spack and making a compiler showdown web page that shows like how fast do these programs run with different compilers and different optimization levels. And I think, we could shame some compiler vendors into fixing some bugs that way.
Yeah, we are going to break the license. You're going to break the usage license of the Intel compilers. They tell you not to report
Numbers?
comparisons with other compilers.
All right. So maybe we don't
If you're
publish
creative
those.
enough, you can do it. I think if you do something relative, you can get away with it, but not hard numbers.
We can, well, we can talk about that. I mean, the absence of numbers for the Intel compiler can at some point be a real motivator for Intel to get some numbers up on the board if it becomes popular, right? You can motivate people this way.
One idea we've had in the EasyBuild community, but it never materialized, is to score scientific software. Like, if it has a test suite, it gets a +2. If it builds with Intel compilers, or is at least aware of other compilers and other MPI, it gets an extra score. And have like a ranking, a public ranking. Whether that's going to turn out really well.
I think, sometimes you just need the development files of a package. So I think it would be nice to somehow be able to separate that. You just need, for instance, the HDF5-dev part of the whole part. So that's a suggestion that I'm not see being possible to do right now.
So can you say that again? I think I missed.
Yeah, sometimes you just need the headers or the development files of a package. So
you mean like a partial installation, like they do in RPMs, and they separate dev and runtime?
Exactly. Yeah, so I think that right now it's not possible to just install that part of a package.
What do you want that for?
Well, because sometimes you just need the whole thing, but just the development part, and I think it will be useful. Just a suggestion.
And in my view, what packagers do in splitting up dev and runtime, I mean, I think they're mostly doing it for disk space reasons.
Yeah,
but they're
just being minimal.
Yeah, but they're making it kind of harder than it has to be, I think. I mean, I think both Spack and EasyBuild just installed everything that the software provides. Headers, libraries, binaries.
Yeah.
Unless you go and strip things down. But
and it's hard to separate that out sometimes because you don't know. Well, I don't know. I mean, it's another type of dependency, right? You're just saying, am I going to build against this? And if I'm not going to build against it, if I've already built against it and I just am going to link against it, then I don't need the headers. So, I mean, we have dependency types in Spack. We could add another dependency type like that and, you know, put a dev option on the different packages. Yeah, we could work it into the model. I don't know if it would be on our immediate list, though.
So, well, thank you so much.
Thanks
For that.